All right, so this week we are going to finish up talking about our tests for convergence. You're going to have a test that we talk about today and tomorrow on Tuesday, and then you'll have another day to work through some of these problem sets because it's definitely one that you want that additional practice for. For the review assignments, as I state in the instructions, I expect you to turn in pictures of the work that you've done on the odd problems with checking that work and corrections as needed. That is still an assignment where you need to turn something in. So get yourself ready for notes and we're going to get started. So today we're going to talk about alternating series. So let's start with what that means. So an alternating series is something that usually will have a power of -1, but what it really means that if you wrote out the terms, you'd have a positive term, minus, plus the next term, minus the one after that. And so when we alternate, we mean it goes positive, negative, positive, negative. Again, this is mostly created by having a power of -1, as we see here and here, but it could also be created by something like, let's say, cosine of pi n, because for every pi n, you'd start at 1, -1, +1, -1. So sometimes you'll see trig ways to write these alternating series as well. Now, to tell if an alternating series converges, the rule basically is that each consecutive term is smaller than the one before. So what that means is that a sub n plus 1 is less than or equal to a sub n. So the value, notice that we're not considering the negative in this case, but that the term itself is getting smaller. And that should hopefully make sense because the idea here is that the limit as n approaches 0 of the terms, as n approaches infinity of the terms is equal to 0. And the reason that whereas before that was the nth test to test for divergence, the idea is that if I start at n equals 0, right? If I start here, I haven't added a term yet. If my first term is positive, right, that means that I'm adding that first term. It's 1. So this is called a finite sum. So this would be sum 1. The next term is negative, so it's going to subtract. But because the value is less than the one before, it's not going to go past 0. It's going to be like, oh, positive, and then back here. But since it's shorter, this is going to be minus that term, and we've got our next finite sum. Our next term is positive again, but it's of a smaller value. So then we end up with partial sum there by saying plus the third term, and so on. And you can imagine that as we keep going, we're spiraling in. And that's why it converges, because as we keep going, we're going to get closer and closer to some number that's right in between here. That's going to be in between 0 and that first term. So, number 1, determine if this is called the alternating harmonic series is convergent or divergent. So if there's two series that I want you to memorize, it's these two. The alternating harmonic series is called that because if I take away the alternating portion, this is called the harmonic series. And the harmonic series diverges by p series because it has to be less than 1, because here p is equal to 1. You could also think about it as p is equal to -1 if you have n to the p without the fraction. So whenever you see this, just remember that it diverges. The alternating harmonic series, on the other hand, we want to ask ourselves, the question is this true? And remember what we do that is we take away this portion, the alternating portion, so take away the power of -1, which means that a sub n plus 1 is 1 over n plus 1, 1 over n. You can cross multiply these. If you're like, oh, I'm still not sure, feel free to cross multiply, and you end up with n is less than n plus 1, which hopefully should feel convincing. You also want to make sure the limit of the terms equals 0 as n approaches infinity. So in this case, the limit as n approaches infinity of 1 over n absolutely does equal 0. So this is convergent. And we can actually be more specific. This is called conditionally convergent, which means that only converges because of -1 power. And we know this is like, okay, well, it's convergent in this case, but only because it's alternating. Because here, if we look at this series without the alternating portion, it diverges. So this is called conditionally convergent, where it's convergent only because of the alternating, versus if it was over n squared, it would still be convergent, but this series would also be convergent if it was 1 over n squared, and that's called absolutely convergent, because it would converge even if you took the absolute values of the terms. A nice thing that you can also do with the alternating series test, and alternating series in general, is you can find the remainder. Now, the remainder is the same as the error between the actual sum of the series, so that's at positive, it has, at infinity, it has no upper limit, versus the partial sum, which is up to a certain point. And the idea here is that the error, the difference in between the total value of the infinite series and the partial value of the infinite series, is less than or equal to the next term. So, because we're always getting closer, each term brings us closer around. So what we can do here is we can say, all right, find this infinite series, but just worry about it accurate to 3 decimal places. So I want to know what I need to plug in here to my calculator, and we'll review that, to be accurate to those places. Now, if it says something accurate to 3 decimal places, that means that the error has to be less than 0.0005, because this here, these 3, and then this would round up if this was 5 or greater. So that would change this 3rd decimal place, and that's why we set the error to that term. Now remember, the error is the same as the next term. So what I need to do here is say, well, the n plus 1 term has to be less than 0.0005. Now using the formula we have here, we have 1 over n factorial. So n plus 1 factorial has to be less than 0.0005. What I often find this helpful is I am going to write both sides as a fraction and then cross multiply. So this is 5 over 10,000, which is the same as 1 over 2,000. So when I cross multiply, we just have to know that 2,000 is less than, not less than or equal to, less than n plus 1 factorial. And this is something that you can solve on your calculator. If you like, I would start plugging in 1, 2, 3, 4 factorial, and you can use that if you go to the math button on most of your calculators. Since the vast majority of you are using TI-83, and then go over to the probability list. And that'll give you the factorial option. And what you'll find is that 7 factorial is the first one that's greater than 2,000. So that means that 7 is equal to n plus 1, which means that n is equal to 6. So what that tells us is that we need to find the series from n equals 0 to 6 of negative 1 to the n over n factorial, again using our calculator, and this will be accurate to 3 decimal places. So again, you're going to use your math button on your calculator for the majority of you, and you can just go to the series summation. Now, some of you will have to go and use sum and sequence as I detailed in a previous video, but most of you will be able to use this and type in here, again using math and probability to get the factorial in the denominator, and you'll get that this is equal to, and we're to 3 decimal places, 0.368. If you have any questions about alternating series using your calculators or any of the tests that we've gone through before, please get in touch.